Good morning, everyone. My name is Weiyou Chen, and I come from Southeast University of China. The title of my presentation is a novel phase error quantitative characterization method for whole-anchor microhemispherical resonator gyroscope. This is the content of this presentation. This presentation contains 5 sections, respectively, are the introduction of the macro HRG analysis of the phase error causes, influence of the phase error, characterization and composition, experiment for phase error, and finally, the summary of this research. First is the introduction section. Mammoth gyroscopes is an inertial sensor used to measure the angle or angular rate. Compared with the traditional gyroscopes, mammoth gyroscopes have the advantage of a small size, lightweight, and easy integration. They have been widely used in both military and civilian fields, such as missile guidance, satellite attitude control, and commercial electronics. Now, the mainstream mammoth gyroscope is the vibration gyroscope. It uses the Coriolis effect to measure an angle. According to the type of the resonator, these vibration gyroscopes can be classified into quadruple mass gyroscope, microhemispherical resonator gyroscope, and a ring gyroscope. The macro HRG not only inherits the advantages of the traditional HRG, such as large dynamic range, higher precision, but also has the characteristics of small volume, low cost, and low power consumption. Figure A shows the fundamental structure of the macrohemispherical resonator gyroscope. This gyroscope is bounded by the macrohemispherical resonator and the planar electrode substrate through the central support ankle. The macroshear resonator is the principal angle measurement unit of the macrohemispherical resonator gyroscope. Figure B illustrates the distribution of the out-of-plane electrodes of the gyroscope. It comprises 16 discrete electrodes for electrostatic drive detection and model turning. The second part shows the analysis of the phase error causes. Figure A illustrates the causes of the phase error of the whole-anchor micro HRG contains circuits. The circuits of the gyroscope comprise the analog circuits and the FPGA digital circuits. Due to the delay in the digital signal processing and the electronic component errors in the analog circuits, the phase error inevitably occurs in the gyroscope. Taking the signal at the node A as the reference, node B to F shows the phase error of each signal processing module. The phase error of from A to B is the phi code. It is the phase error caused by the digital signal modulations. Phi DA is the phase error of the DAC. Phi OPA is the AC-DC coupling phase error. Phi CV is the conversion circuits phase error, and phi AMP is the front-end operational amplified circuits phase error. Figure B shows the simplified forms of the phase error. Here, delta phi P in equation 1 is the detection phase error caused by the CV conversion circuits and the front-end operational amplified circuits. Delta phi F is in equation 2 is the fluctuation phase error caused by the digital signal modulation TAC and AC-DC coupling circuits. Consequently, the total phase error of the micro-hemispherical resonant gyroscope is the delta phi PF. It is the sum of delta phi P and delta phi F as shown by the equation 3. The third part presents the influence of the phase error. Equation 1 shows the drive forces of the whole angle mode when the phase error exists. By expanding equation 1, we obtain the equation 2. It can be seen from equation 2 that the phase error causes the coupling errors between the control forces of the whole angle macro HRG. According to the equation 2 and the average method presented by Dr. Lynch, we obtain the equation 3. The equation 3 shows the dynamical mode of the whole angle mode containing phase error. The phase error mainly affects the orthogonal control loop and the angular velocity detection loop. As shown by equation 4, the phase error causes a DC bias in the orthogonal control output that is related to virtual Coriolis force, FQS. As indicated by equation 5, the phase error causes the sinusoidal fluctuation error in the angular velocity output that is related to the frequency difference. We can observe from equation 4 that the DC bias of the orthogonal control output satisfies a linear relationship with FQS, and the linear scaled factor is minus 10 delta phi PF. Consequently, according to this relationship, the phase error characterization can be realized, as shown by the equation 6. Figure A shows the simulation result of the angular velocity fluctuation error and the different phase errors. The angular velocity fluctuation increases with the growth of the phase error, and the fluctuation phase does not change and maintains the sinusoidal phase. Figure B shows the vibration of the orthogonal control voltage with the virtual Coriolis voltage, VQS, and the phase error equal to minus 10 degrees. The orthogonal control voltage exhibits a linear relationship with the VQS. These simulation results are consistent with the theoretical analysis. The fourth part performs the characterization and the compensation experiment for the phase error. Figure A shows the phase error compensation method based on the phase error characterization result. The phase error compensation is achieved by calibrating the demodulation reference signal phase. Figure B shows the equipment used in the experiment. We first perform the phase error characterization experiment by using the presented method. The green line in figure A shows the relation between the DC bias of the orthogonal control voltage and the VQS before phase compensation. It can be seen that the orthogonal control voltage DC bias is linearly related to VQS, and the linear scale factor is 0.239. According to this result, the phase error is characterized as minus 13.44 degrees. Importing this characterization result into the phase error compensation module, the phase error compensation is realized as shown by the red line in figure A. After phase compensation, the orthogonal control voltage DC bias is basically 0 and no longer changes with the VQS. This result confirms the effectiveness of the proposed phase error characterization and compensation method. Figure B shows the angular velocity fluctuation of the whole ankle macro-hemispherical resonator gyroscope before and after phase compensation. It can be seen that after phase compensation, the angular velocity fluctuation error is significantly reduced. The zero bias performance of the whole ankle macro-hemispherical resonator gyroscope before and after phase compensation was tested. As shown in Figure A, after compensation, the zero bias stability is reduced from 3.8 at 33 degree per hour to 1.565 degree per hour. Figure B shows the Anlan variance curves plotted according to the date in Figure A. After compensation, the zero bias instability reduced from 0.8649 degree per hour to 0.4162 degree per hour. It can be seen that the phase error compensation can effectively improve the performance of the whole ankle macro-hemispherical resonator gyroscope. The final part is the summary. The main contents of this research are reflected in 3 points. One, we established a dynamic model of the whole ankle mode containing phase error for the first time. Based on the derived model, the influence mechanism of the phase error in the whole ankle mode is clarified. Two, we proposed a novel phase error quantitative characterization method for whole ankle macro-hemispherical resonator gyroscope and realized the phase error identification. Three, we performed the phase error compensation experiment. The experiment result confirms the validity of the presented error characterization method and the established dynamic model. That is my overall presentation. Thank you for listening.